axons, yeah? Where are the cell bodies? In the retina. So this layer here will be the cell body. Cell body, agree? Okay. Now remember, how about receptors? What part of a neuron would be receptor? Dendrite, cell body, or axon? Dendrite. Okay, dendrite. Which means the photoreceptor, right? Photoreceptor will be where? In the retina here. Does that make sense? It has to be dendrites to the cell body, then the axon. You told me all these are axons, correct?
Yeah.
Now, if these are the cell body and that is the dendrite out here, are there any cell bodies here?
No.
Negative. Are there any dendrites here?
No.
Negative. Which means, are there any photoreceptors here? Negative. If there are no photoreceptors, can we see when we pick up light in this area here? So that's why we call this your blind spot. So even if light shines here, we can't pick it up because there's no photoreceptors. Does that make sense? Okay, does that answer your question back there? Okay. All right. So.
It's true. You try it.
So here's up close and personal to the retina. I'm going to give you a minute to look at this. So where's light shining in? Where's the path of light? Show me with your hands. Where is the path of light? I'll make it a little clearer. Let's start with the light from outside. And it's going to come into your eye. Okay, let's show me the path of light from outside coming into your eye. Which direction? Correct. Okay, so it's this direction. Agree? So light is somewhere down the ground. This is one giant eyeball. We're only looking at the retina. Okay? One giant eyeball. So the pupil is somewhere in the ground. And the light's coming in this way. Does that make sense? So light's coming in this way. The end of the retina is here, because this is what? This is what layer? Choroid, right? Vascular layer, right? Make sense? Red and blue, vascular layer. That's the choroid layer. So the retina starts here. So light shines here, but where are our photoreceptor? All of this. So this layer here are our photoreceptors. So light comes in and it will stimulate these photoreceptor cells. Okay. How many different kinds of photoreceptors do you have? Three? Two. 3, 2, 1, what? 2, 4, or 5?
2.
According to this picture, how many kinds do we have? Show me with your finger. Okay, most people say 2, yes, and they are what?
Rods and cones.
Yes, rod and cones. How remember this? C for cone, C for color. Gee, so what do you think rod does? Black and white, yeah, light and dark. Okay. So cone is responsible for your light and dark sensation, and cones are your color receptors. Okay. All right. So anyway, so light comes in, stimulate the photoreceptor first, and then that will synapse to this layer of cells, which are neurons, yeah, these are neurons. Ah, what kind of neurons are these? Look at the shape. Once upon a time, we had,
Bipolar.
what kind of polar?
Bipolar.
Yes, bipolar. What does bi mean?
Has two ends.
Two, yes, and it's perfect, right? There's one end here, one end here. So what end is this? Is this a dendrite or axon end? Dendrite end. This is the what? The cell body, and this would be the axon. Yeah, so we have bipolar cells, bipolar neurons to be exact, in the retina. See? Bipolar cells, bipolar neurons. These guys, the red guys. We have horizontal cell, okay. Then we have these cells here, ganglion cells. I don't know why they call it ganglion cells, but anyway, let's pick that. Okay, but then you see how all their axon forms this yellow layer here? All the axons of the ganglion cells, and then it becomes the what? All these axons become, when it exits the eyeball, it becomes the optic nerve. Okay, optic nerve. Make sense? Okay. So we call it optic disc is the blind spot because it lacks photoreceptor. That's all it is. Lacks photoreceptor. Okay. Now, I've pointed out fovea centralis multiple times. Why? Because it's important. It's that pit, right, that sunken area. Because it's why? It's your sharpest vision. Your sharpest vision. Okay. Why is it sharpest vision? Highest proportion of cones and almost no rods. No rods. And you can see it, you know, when this is what an ophthalmologist or optometrist do when they look in the back of your eye. They just look in the retina. Here it is, the optic disc, because you see the blood vessel coming out of it. So that tells you the optic disc. And then just to the side of it is the fovea centralis, and that's where you have the maximum density of rods. I'm sorry, of cones and very little rods. That's your sharpened vision. So in other words, when you stare at something, that's where the light's gonna shine. Right there, fovea centralis. Light's gonna shine here when you're staring at something, because that's your sharpest vision. Everything else is peripheral vision. Right? You still see it, but it's not gonna be as sharp. Okay? And then this little picture, just to test for your blind spot, which you might have done in a biology class. Okay. Something that interesting is, do you guys know that we see everything upside down?
Yeah.
Yeah. And then the brain just converted it right side up. So the brain adjusts. Oh, what lobe? What lobe the brain will adjust it up, right side up for us? Occipital lobe. Very good. Occipital lobe. Okay. So yeah. So here's the path of light coming in. See how the lens flattens versus the lens round up. Remember how we're talking about how the lens focus change shape from fatter to skinnier lens? Because when it's skinnier, you're using it for your distant vision. And when it's fatter, you're using it for near vision. Okay. Near vision. And if you notice, you see how this accessory ligaments all relaxed? Because is there tension in them? No. Why is it relaxed? The ciliary muscle is moving toward the ciliary, moving ciliary body toward the lens. So whereas here is relaxed so that there's more tension in the ligament. Okay, so it changes the shape of the lens is basically what. Yeah.
Can you exercise the ciliary muscle?
Yeah, believe it or not, there are some ophthalmologists that will teach the exercise that would try to improve your vision. So yes, there are eye exercise that will supposedly help.
Does it help?
Well, they think so. The ophthalmologist thinks so.
Do you think so?
Well, I don't know. I'm not an ophthalmologist.
The this one.
But, you know, it's based on the idea of muscle contraction, right? And we know that we can exercise skeletal muscle to build bulk. So why not exercise your ciliary muscle? So the thought is there, and it could make sense. So it could improve vision. Okay. All right. Let's move on. Say so visual pathway. You don't have to know this. I won't ask you, but it's interesting to know. Because this is more physiology. But I want you to understand why we teach you this terminology, because it's involved. Okay. Here's your field of vision. So everything in here would be from your left eye. Everything here would be from your right eye. When you're in the middle area here, you see for both eyeballs. Okay? And so blue is the left eye, red is the right eye. So right here at the optic nerve, remember optic nerve? This would be all from the left eye, this all be from the right eye. And then it crosses, it crosses. Remember chiasmatic groove? Optic groove on what bone? Sphenoid bone. It's allowing this X to cross, to lay to rest, okay? So that sphenoid bone is allowing the chiasm is the X, okay? That's a chiasm. The crossing of the right and left optic nerve. Why? Why do we cross like that? Look at the picture. Why do you want to cross like that? Because, look at this picture.
To flip the image right side up.
I'll give you a hint. Follow the blue and red line. What the blue line? Blue lines are from the left eye. Red lines are from the right eye. Follow the blue and red line. What's happening?
Both sides of the brain.
It crosses over, right? Why? Why do you want them to cross over?
So you see one picture?
Where is the ultimate endpoint? Occipital lobe, which you already know, yes? This lobe, does it get information from both eyeballs?
Yeah.
This lobe does get information from both eyeballs. Isn't that better than you just have one line going down? Yeah. One line going down would be, this lobe won't get from the left eyeball, this lobe won't get from the right eyeball, agree? Which is not superior, because what if something happened to one side of your brain? That's it. You lost the vision, right? You guys understand? So this crossing is beneficial to us because now you have both lobes of both sides of the occipital lobe seeing from both eyeballs. And that gives us binocular vision. What's binocular vision? Depth perception, right? You can see something is closer, something is farther. That's binocular vision. With 2 eyes, you can see depth. You guys ever cover one eye? It's much harder to have depth. It's harder to know just how far away something is when you only have one eye. But when you have 2 eyes, it's a lot easier to have depth of view. Anyway, funny story, okay, which I will always remember about depth of view. So, back in the medical school days, as a med student, you get to scrub in, which means you wash, you gown up, and you're right there at the operating table with the surgeon and the nurses. But everyone knows you're like the low man on the totem pole, right? So you do what's called scut work. And they put you there so that you can sense what it's like, and when you really hardly do anything. So one of the job that med student can do is retract. So you sit there and you hold the retractor to expose the surgical field for the surgeon to operate. And so you're just a holder. Then every once in a while you have to cut. You don't get to cut the patient, you get to cut the suture. Okay? And so I remember it was a day where I had a problem with one of my contact lens, and at the time I was wearing contact lens. So I decided to go one eye without contact lens. So I was blurring one eye, clear in one eye. Bad perception, depth of field, right? Well, I didn't know. So I said, okay, you scrub in. Oh, great. So there I was retracting, and then the surgeon tied the knot, held up the suture, handed me the scissors and said, okay, I want you to cut 1/4 of an inch. What the heck? 1/4 of an inch, right? What am I gonna do? Like whip out a ruler and, you don't do that. So I'm like, okay, cut. 'Cause you can't really tell 1/4 of an inch when you only have one eyeball. That's good, right? And the surgeon, total typical surgeon mentality. I said 1/4 of an inch, not 1/2. Hey, what a jerk, Total. 1/4 of an inch, 1/2 an inch is minuscule, right? But and like I said, it's a funny thing looking back now. But it taught me depth of perception, depth of field, because I only have one contact lens in. Of course, I didn't tell the surgeon that. He was like, "Why are you walking around with one contact lens in?" Anyway.
Wait, so why did you have one contact instead of?
Because it was irritated. One of the contact was irritated, and I didn't want it to rub on my cornea, and I'd be all, one eye irritated the whole day. Yeah. So I just said, yeah, I'm just gonna wear one contact lens rather than both. So anyway, more of the story. Don't do that. So then we talk about the two chambers, you gotta remember, and the two cavities. Yes? Please be careful. What's a cavity and what's a chamber?
Cavities and sides.
Cavity, which is bigger, cavity or chambers? Yes, cavity is bigger. Chamber is the subdivision of the cavity, right? Okay. So easy to get confused, that's why I want to show you this picture. Everything here would be what? Cavity. This specifically is the chamber. This would be the chamber, and back here would be all cavity. All right, all cavity. Okay. Now, why is this important? Well, there's something called glaucoma. Glaucoma. We call it closed open. So we have aqueous humor in the anterior cavity. Yes, remember liquidy? Okay, and you can read about what makes it. Epithelial cell come in the ciliary body, makes aqueous humor, and it flows. It flows here from the posterior chamber to the anterior chamber. Make sense? Okay, so it's made here, and then it flows here to the anterior chamber. Okay. Now, why does it go out there? Because there is a drainage right here, number 3. Drain into the sclerovenous sinus. Get it? Scleral because this is the sclera. Venous, what's venous? Veins, which is blood, agree? And it's a space, a sinus, so the veins gonna drain it into the veins ultimately. So what does that tell you? Aqueous humor is more like blood plasma, right? Similar to blood plasma. What else do we talk about? CSF was like blood plasma, right? So the recurring theme, blood plasma, we build it, go back to blood plasma. So there is a canal of Schlemm. I saw it earlier, but I don't see it now. Canal of Schlemm is the way to drain. And anyway, what's the point? The point is, if that canal of Schlemm is blocked, will there be pressure buildup? And that lead to glaucoma. Glaucoma is when you have high pressure in the eyeball, yeah? And what's the danger? So what if you have high pressure in the eyeball? Your eyeball is just, bulging.
Lens can't retract and get bigger, right?
It will do what? Try to go back to the eyeball. There you go. So if you have a lot of pressure, will that put pressure here?
Yes.
And now what happens to these little blood vessels? They'll be slammed, yeah? Will blood flow through? Would that make the retina very healthy? And that's why it leads to blind. stimulation of these retinal cells, the neuroreceptors.
How can you fix that?
Medication is one, and
What
if
is
that
the
doesn't
medication?
work, I'm gonna try to do surgery to open up the canal schlemm. But yeah, so glaucoma is increased pressure in the eyeball, and you're pressing down on these vessels, and that will ultimately starve the retina of blood supply, and that's blindness. It's the end consequences. Okay, another popular disease is cataract, yes? You guys know what cataract is?
Well, not exactly, but I know it looks.
Okay. Cataract is when the lens gets cloudy. It's like a dirty window. So what they do is the lens, it doesn't show it here, but there's a sac that holds the lens. So the ophthalmologist comes in, make a incision in the sac, take the old cloudy lens away, and slip in an artificial lens into the sac, sew it up, and that's it. That's cataract surgery. Okay. It's the cloudy lens getting replaced by a new clear lens.
When they do laser surgery, what is that?
Yeah, laser surgery is using laser to cut, because laser with machine is much more precise than our little hand. You're talking about a little tiny area here, right? So we control the laser machine to make the more precise cut. But even with that, you need steady hands. That's why if you're interested in surgery, you really need steady hands. Otherwise, it's not good for your patient, for obvious reasons. Okay, and then of course, vitreous humor is the jelly stuff, okay? All right, so we're now gonna go to the ear and finish this off. This look familiar? From lab this morning, right? We have outer ear or external ear, middle ear, this whole area here, and then inner ear. Yes? Okay, now the inner ear is in the bony part of the temporal bone. Remember that ridge where we have the internal auditory meatus here? That whole ridge is all bony, you can't see it. But that's where the vestibule, the cochlea are housed, in that bony ridge, okay? That ridge. It's a little bit of a hollow cavity inside to hold these various structures, but otherwise it's all encased in bone. And then of course we connect the middle ear to the eustachian tube, right, auditory tube, we talked about that already, okay? All right, and then cranial nerve 7 and 8 comes through here, the same hole, but we focus on 8 because it's the vestibular cochlear nerve. Vestibular cochlear nerve. But yeah, 7 and 8 goes through the same hole. Okay. Believe it or not, there's a little tiny muscle in here. I did not put it on your lab list because we don't have a model that shows you the little muscle, but we do have little muscles along with the ear bone. Should you recognize these ear bones by their shape? Yes, because I have individual ear bones that I could put on the test, okay? In the lab, you guys have this model where it's kind of a clear eardrum. That's a tympanic membrane, and usually a clear eardrum, separating the outer from the inner, from the middle ear. Okay. Make sure you know the name of the 3 bones. And by the way, I want you to know them by their anatomy name: malleus, incus, and stapes, okay? The hammer, anvil, and stirrup, that's the layman's equivalent. So make sure you know them by the anatomy name.
What if we forget and write that one?
Well, let's hope you don't.
Me and
It'll be partial credit, okay, but it won't be full credit. Okay, so let's move into the middle, inner ear. All the good stuff is here, okay? So, the outside is the bony labyrinth, okay? And then the inside is the actual membranous labyrinth. So it's protected by this bony labyrinth on the outside. Does this look familiar? The snail shell, the cochlea, vestibule is this whole thing here. For anatomy lecture, you have to understand the vestibule has saccule and utricle. So saccule and utricle makes up the vestibule. It's not on your lab list because we don't really have models that breaks it down to this detail. But for lecture, the whole thing, vestibule, comprised of utricle and saccule, okay? And then we have two windows. What are their shape? Oval and round, right there, the two windows. And then, of course, with the utricle, you have the semicircular canals. Now, we're gonna cut through a loop right here of the bony labyrinth, the semicircular canal. Now you see what I call a bony labyrinth? It's all bony, right? It's all bony, and inside is the membranous labyrinth. These little red lines, that's the membrane. And we have lymph, lymph. What the heck is lymph? Weeks ago, it was fluid. Came from where? Plasma. And it ultimately returned back to plasma, right? And what chapter was that? We'll talk about lymph. The lymphatic chapter, yeah? Right? Don't think too hard. Lymph was in the lymphatic chapter. Okay? So today you see lymph again. So you can kind of guess it's going to be very similar to plasma. Agreed? But it's in your ear. So we have perilymph, endolymph. Okay? Two different locations. Let's take a cut through here, through the cochlea, just one ring of it. Same deal, bony labyrinth, and inside is your membranous labyrinth, right? Three distinct sections. You can call it duct or scala, right? Remember this? Scala, what? Tympani, vestibuli, and cochlea duct, right? Cochlea duct. And it's had same deal, perilymph as well as endolymph. So let's look at the details. I'm gonna kind of just really quickly run through this because it's more physiology. You'll get it next semester. At the base of the semicircular canal, we have hair cells. Looks familiar? Hair cells. And connected to the hair cells are these yellow things. What's these yellow things? Nerves, right? What part of the nerve? Axon, right? So these are hair cell connected to neurons, axon. And so what kind of receptors are these? Hair cell. Last time we saw a hair cell as taste and smell, right? And that was what kind of receptor? Chemoreceptors. Today, today with hearing, they're a mechanoreceptor because when we turn our head or when we move, do you think these hair cells are moving? Yeah. So when they move, it will stimulate the neuron and tell the brain your body's moving relative to the external environment. So the hair cell mechanoreceptors, okay? And the rest, like I said, you're gonna learn in physiology. But for you, right now, just know that we have hair cell. See, little hair cell sticking up. There is a jelly-like layer with little tiny stone called otolith. And so when your head is upright versus when you're nodding, you see how the hair cell moves? Mechanoreceptor. Stimulate the nerve, tells the brain what's going on. All right, let's talk about hearing. It says cochlea, and the most important part of a cochlea is the organ of Corti. Okay, so I'm cutting through one loop of the cochlea, and those are the three scala that we mentioned in lab, you guys remember? Scala vestibuli, scala tympani, and this whole thing here is the organ of Corti. This is where hearing is gonna start. And it's in the cochlea duct, okay, cochlea duct. Okay, so we call it organ of Corti. Another name for it is a spiral. Synonymous. And here you go. Here's the picture. All of these are on your lab list. Okay. Tectoral membrane is on top. Can we have that model? Then you have little hair cell. And then connect to the hair cell, you have the nerve becoming axon here, and that goes to vestibular cochlear nerve. So whenever these hair get bent, and why do they get bent? Because sound wave travels through the canal, vibrate the membrane, tympanic membrane, moves the three ear bones, and ultimately goes here. Okay, let me kind of go back to the ear structure. There you go. Sound wave coming in, vibrate the tympanic membrane. The three bones are all connected, so when this starts to vibrate, the bones will vibrate. That put pressure up against the oval window. There are, remember, lymph in here, fluid, lymph. And when you have vibration, that will move the lymph. That ultimately moves the lymph in the cochlea. That will then move the tectoral membrane, which will then move the hair cell, right? The hair cell to the tectoral membrane. And then the hair cell will send the information to the axon. And we hear. Axon goes to what lobe? Hearing is what lobe? Temporal, yes, temporal lobe. And we hear. So that's my short version. Okay. You get more when you get to physiology. But like I said, with the vibration, it's going to move the lymph, which will then move the tectoral membrane, which will then bend these little hair cells, stimulate the nerve. That will then be sent to the temporal lobe, and the brain will then determine what is your hearing. It's all mechanoreceptors. So, let's talk about deaf. What do you think is going to damage these? If you damage these hair cells, can you hear? No, because nothing's going to be bending, right? You don't bend these little hair cells because they're not there. Can you stimulate the nerve? Negative. So what kind of stuff might damage these hair cells? Loudness, yes. When you expose your ear to loud decibel, like really loud noises, especially on a continuous basis, you damage the hair cell, and they don't come back. Okay. So you lose a hair cell forever, and then your hearing starts to decrease after that. Okay. And so it's all the hair cell. There's some pretty cool picture. I don't have it here, but you can Google hair cell damage due to high volume of sound. Yeah. Not unless it's like incredibly high pressure where it hurts the ear, that might, but the hair cell is more vulnerable to loudness than pressure. I mean, the pressure will probably blow your eardrum, blow your tympanic membrane before it goes this deep. And so that's a totally different issue. All right, does that make sense? Okay.